a software coder. I've been around for a long time. And then after that, we're going to talk about how to configure your robot, what the coder laptop looks like, and the drive, the Gyro drive code, and the framework that I'm going to give you as a starting point. Okay? So I'm a professional engineer. I've been writing software since before PCs were invented, if you can imagine that. There were no PCs. Not only were there not phones, there were no computers when I started programming. So I programmed on cards, a card deck, and would go into a machine reader and would suck in the cards and go and then print out on a printer. And the paper would come out and they'd tear it off and hand it to me. And that's how I figured out how to write code. So I've been doing it for a long time. I spent 4 years doing FRC code, and so that's where I come from here. So I've done 4 years of FRC coding, and this will be number 5. We have worked on the Toronto Code as a group called the Toronto Coding Collective. So it started as a collaboration between 1310, Runnymede, that's our team, 2935, which is NACI, 854, the Iron Bears, and 5834, R3P2. And we all got together and we started coding for our robots as a group, because let's face it, FRC code is really hard. We wouldn't see so many robots just sitting there and autonomous doing nothing if it was very easy. It's not easy. We understand that it's not easy, and it's really complicated. So as a group, we got together and we started sharing code. And eventually what happened is in 2017, I took all that code that we've been writing over the last 2 or 3 years and put it together on a website called the Toronto Coding Collective. So www.torontocodingcollective.com. And that's going to form the basis of what we do today. So here's your Q&A questions. What do you want to talk about? I want to talk about where I start. I want to talk about what is command-based programming. I want to talk about VS Code. How do all the pieces fit together, which is kind of going to be covered under where do I start. Debugging is something I'm going to get into when I actually talk about the Gyro drive code. So we have code that follows a gyro and walks in a dead straight line in autonomous for a specified distance and stops. Turns to another angle that's well defined, walks that angle, and then stops at the right spot. It will do the auto perfectly every time. Guaranteed. You will get there. So that's what I want to see. So that's the whole purpose of this, is to raise the level of auto. You shouldn't have to write code to make the robot drive. The robot drive is pretty solved. It should be pretty solved right now. What you're going to have a hard time with is doing this auto pattern. You're also going to have a hard time with making the superstructure pieces. And so by providing you a command-based framework, I'm hoping that it makes these superstructure pieces a little bit easier. And we'll talk about what that is. So the Toronto Coding Collective website, here it is. I don't know if you can see it from there, but it's dedicated to developing FRC robot code using the command-based programming in Java. That's it. That's what we're here for. Right? So how do we use Java to make this robot sing and dance? We want it to do exactly. Awesome. So we're going to extend the basic functionality available in some of the WPI lib examples. So there are WPI lib examples out there of a command-based robot. And you can say new example, command-based robot, and it does nothing. So what I want to do is give you a command-based robot that does something, and it does at least this. So our hope is that the Toronto framework will allow rookie teams to build reliable code with ease. So we're going to spend the entire rest of the day on this website. And I'm going to be taking you through this website. I'm going to pull up code examples in VS Code. And we're going to run the robot, and I'm going to show you different things, different reasons why we build certain things, okay? You can contact me. It says contact us. Right now, there's only 2 people on it, me and my daughter. But you can contact me through Github. And if you click on that link, it takes you to Github. And if you type in a message, it's an online chat. So I will there, and I will get, if you did it now, my phone will probably go off. Hopefully I have it on you. Okay. Changes for the 2019 season. Now here's the ugly part. Ugly, ugly, ugly. Changes for the 2019 season. We're moving from a very professional tool called Eclipse, which every software house almost in the world uses, including mine. I have a software company. I write software professionally. We're moving from Eclipse to this lame editor. This is an IDE. This is a development environment. This is an editor, like a text editor, called VS Code. VS Code does nothing. Eclipse does everything, and VS Code does nothing. It's not a good choice. However, VS Code has this big market space. So you can go there and search forever to try and make VS Code do what you want it to do. You can install any plugin you want made by Sammy Jones or Adil C or the best programmer. I have no idea what those plugins do. I don't trust them and I don't want them. There's one plugin for VS Code that I'm going to show you, and that is the Red Hat plugin to support Java, which you will need. Okay. So on the website, I know you can't, I've kind of blown it up to be really big. There's this nice friendly button that Asha teases me about because it looks really ugly. It says start here, right? Nice friendly button, start here. When it comes back up, I'm going to click the button. This is really weird. Does anyone know why this is doing this?
No. You can check it out. Why the projector goes on and off.
Yeah. Let's start here. You don't know, I know. I don't.
It does funny things.
It does that.
Like throughout school.
I get it. Yeah. Okay, so here's some more descriptions. So this is our homepage, right? So I just told you it's got the purpose in nice friendly letters up above, which we read. It's got the changes coming, which we hated. And now we're down here to start here. Okay, so start here. So start here. So one of the questions that I've been asked is, do I need this? Like, why is this really important? There's two sections on this page. One of them is for drivers, which is actually for robots and their drivers. So I should rename this. It's not really for drivers, it's for robots and drivers. And this is all the tools that you need in order to make the robot go. Okay, so you got a driver station and you want to configure your robot so that you can download code to it. You haven't written any code yet, but like you've got a radio, you've installed the firmware, you've got it wired up, you've updated and upgraded everything. You can connect to your robot. You can do all the stuff, right? So this is for robots and their drivers. Coders don't need that. You don't need it as a coder. In particular, if you have a Mac and you want to code on a Mac, you want to do this for coders if you're Mac-based. But if you're PC-based, someone has to eventually connect to the robot. So the Mac can download code to the robot, but something has to run the driver station and actually connect to this robot. And that is this piece. Connecting and driving, development. Okay? Do I need this? So I'm a professional, I've done this before. Do I need it? Yes. Whether you're an experienced team or complete rookies, you always need to install the latest and greatest from first. So let's say you went home and you said, oh, I heard about this Toronto Coding Collective Framework, I'm going to install it tomorrow, I'm going to do it. And you install it, it's not going to run until you redo these steps in the season. So on January 1st, they're going to release an update to the firmware, they're going to release an update to all the libraries, they're going to change a whole bunch of stuff, and I'm going to go as fast as I can to post it on this website for the end of the first week so that you can be up and running by following the instructions that are here, okay? Right now, this is the instructions as of today. If you're gonna get your robot up and running with the alpha version of the deployment in VS Code for January, you can do that today on this website, but you will need to do it again as soon as the challenge is released, okay? So the reason that I asked sort of where you guys wanted to go at the beginning was because I didn't know whether we should be clicking for robots and their drivers or for coders as our first button that we're going to click here. But a bunch of people have asked for the complete overview, especially you guys you need to know about for robots and their drivers. So I'm going to quickly go through robots and their drivers, and then we're going to go over to coders. So this is the station that's connected to the robot, must be a Windows machine, cannot be a Mac. There are third-party stuff for Mac, highly, highly not recommended. Use a Windows machine to connect to your robot with the official software.
Can you use boot camp?
What?
Like, are they talking about like boot camp that you run it, or like boot camp when you can?
I don't think it's on Robotics.
I wouldn't do it. Don't do it. Like you don't want to. You can't do it in the tournament anyway. The driver station in the tournament, the field, won't connect to a non-Windows machine. I'm saying that we have problems connecting with a Windows machine and we can barely get support. If you go to a non-Windows machine and try and connect it to the field and something goes wrong, they're going to hand you a Windows machine. Right? They will not support it. So on this page is very long, and you know, I guess I could shrink it down here for a second. I could if it didn't do that, but here, I'm going to shrink the page way down into micro size so that you can just get an idea of the scale of it. So on this page, you're going to install National Instruments stuff, you're going to configure your RoboRio, you're going to do the RoboRio imaging, you're going to flash your radio, which probably isn't going to work, and you're going to do that 4 or 5 times until it finally works. And then you're going to do the CAN firmware and install some CTRE stuff, and then there's some more stuff that you need to do. Okay, so that's kind of the overview, but let's go through some of those pieces one by one, and I'm going to blow it back up. So the size you can see, which I think that's good, right? So again, it just says these tools are not required for developers, but install the National Instruments Update Suite. So this will come out on July 1st. When you go to this spot on July 1st, it will be encoded. It will be encrypted. January 1st. January 1st. When you go on the release date, January 5th or 6th or whatever it is, the update suite comes with a password to unpack it. Don't wait until the day of the tournament to download this. Download it like 3-4 days in advance. This site gets congested on release day, and you still have to use the password, the encrypted password anyway for a couple of days until they update the website. So download this a few days in advance. So you go to the download the update suite, and it takes you to this page, and here's the FRC update suite for lab use. And they want my feedback, but no thanks, not right now. I'll help later. And then you click download. So it'll say 2019 obviously here when you go and download the one at Christmas or after, and it'll be zip protected, so you won't be able to unzip it.
Richard, how far in advance do they post it on the website? Like a week in advance or a month in advance, or?
About 4 or 5 days. Not that far. Yeah. So right now you can still download the 2018, right? So then you need to update the RoboRio firmware. So there's a tool that comes as part of this package to update the RoboRio firmware. And I'll just go there quickly, just to show you what it all looks like, because we have 90 minutes. So there's a RoboRio imaging tool. And when you start it, just does this, and then it starts scanning for your target. So the RoboRio imaging tool allows you to set your number on the RoboRio, right? The firmware update, before you do that, sorry, I kind of went a little bit in the wrong direction. direction there, requires Internet Explorer of all things. You can't use Chrome, you can't use Firefox, you can't use any of the modern browsers, Edge or anything. You have to go to a Silverlight supported Internet Explorer, and then if you're connected with the USB cable, the address is 172.22.11.2, and it describes all this on the website. And the reason that you need to do this is you need to be able to click this update firmware button. You log in and you update the firmware, and then you're allowed to download the image. So the firmware is at the hardware level. The image allows you to set your team number and connect to the FMS. So there's those two layers, right? Hardware and then team number layer, and then you can load your software on top of that third layer, okay? And all this is described in meticulous detail, step by step, on the Toronto Coding Collective website. So update through the web interface, start Internet Explorer, yes, you got that right, don't use Chrome or Edge, can't be used. Safari, you're not even on the right platform. Image the RoboRio through that imaging tool that I just showed you, configure the radio, and then you have to update the CAN bus tools. So it's interesting that the National Instruments, they don't actually supply the CTRE CAN-based devices. So there's at the very minimum, every robot must have an electrical power distribution panel, and that's connected via the CAN interface to the RoboRio, and you have to update the firmware on that. There's firmware on there that allows them to read the power consumption of your robot and the voltage level of the robot. So you have to update that. You also have to, if you're using pneumatics, have to update the pneumatics tools. If you're like us and you use CAN-based devices, then you also, so you have to update these two. You also have to update all of the Victor and Talon that you're connected to via the CAN bus. So you have to update the firmware on all of these speed control devices.
Is it possible to do those updates without the RoboRio? Like, is there any way to do a direct connection? It has to be
Not that I know of, because this dashboard comes up from the RoboRio, so it's loaded onto the RoboRio. It's installed on the RoboRio, and when you connect to that device, then you get this. I don't know of a way to do it directly without a RoboRio. You showed me a Spark thing, and it seems like they're setting up to be able to do it without a RoboRio.
The Spark Max has a USB-C connector, so you can control directly from your laptop while you're doing prototyping.
Right, and that makes sense because this is all CTRE, so they would have had to gone to CTRE and ask CTRE to put their device on this list, because this is all across-the-road electronics version of updating the CAN bus, right? They control the CAN bus in some way. Okay, that's it. That's all I'm going to say about here's how to download stuff to your robot. Oh, last piece is there's a smart dashboard. So the smart dashboard looks like this and gives you information about what's going on in your robot. Surprisingly, it doesn't come with the National Instruments tools or the CTRE tools. It comes with the development tools. So remember I said you don't need to install the development tools at your driver station? You don't, but you need to get these pieces of software onto your system. You can either just download and install the development tools on your driver station, so you can take that away with you and have it in the queue, or you can, if you were us, you would have had someone with a Mac that was downloading software, and then the other PC would have had to have had these jars installed manually so that you could run the driver station. I don't know what's coming in 2019. I found that all very awkward, and I'm hoping that they do something else in 2019. Okay, so we did the start here. So the next part is development tools, and let's go on to that. For coders, so the first thing you install is the Java development kit. Small thing, you have to be Java 11 this year. You can't be Java 8. Oracle's changed all the licensing for Java 11. Now there's a paid subscription model for professionals, and then there's this OpenJDK 11. It's all a kerfuffle. Go to the javanet.site, and I use the OpenJDK, this one, right now, for our development. Install Visual Studio Code and configure for Java. So you go here, you download Visual Studio Code. Looks like this. You go here, and it's got, you know, VS Code. You download and install it. And then you go and install the extension packs in VS Code. So I might want to show you a little bit about the market space and the extension pack thing, just so that you have a familiarity with how it looks when you're going to go in here. So here's VS Code. I'm going to bring it down a little bit so you're here. There's this button icon over here, extensions, and you can go here and search for extensions. So right now I've got all these installed. These are the ones that are installed, and then this is what it's recommending below here. So it's kind of going to recommend all kinds of crap for you. But the way that you get here is you type in something like, I'm going to go back to the website because I forget, Java extension pack. So when you type in Java extension pack in VS Code, it starts looking for that. So Java extension pack. And there it is. It comes up, and it says Microsoft, because Microsoft bought Red Hat. It used to say Red Hat 2 weeks ago. Now it says Microsoft because they bought Red Hat. But yeah, you would install. This is the one that I've got installed here, and then you install that, and it installs other plugins to support Java. So natively out of the box, there is no Java support. Then, unfortunately, you still have to do more configuration with VS Code to get it to recognize and work with Java, and you need to configure VS Code to use the installed JDK. So again, in here under File Preferences Settings, you can do searches for java.home, and it'll show you that it's empty by default. You have to go and figure out where you've installed the JDK 11, copy the C address, go into VS Code and install and copy those configurations. It's not hard to do. Just be patient, read carefully, go through it. It's slow. It'll take all day. I get it. We're not in Eclipse anymore. Is what it is, right? So you just follow the instructions here. So configure VS Code to autosave. That's always a good thing if you want to save your work before you deploy it. And then it tells you to create a sample project, do all these, do a bunch of other stuff. Now we get to GitHub. So do people know what GitHub is? Does everyone know what GitHub is? It's a cloud repository for code. So there's a lot of code in the cloud, and you want to save your code up to the cloud so you can share it with your friends. So your friend has a GitHub account, you have a GitHub account, you're both connected to the same repo. Someone pushes something, someone else pushes something. You can see what everybody's pushed, and you can download and accept their changes, right? GitHub, really great place to store your code. Last thing you want is the code to be stored on somebody's personal laptop with no copy in the cloud, not anywhere else, and you're going to take that to a competition and they fall and drop their machine. Now what do? Nothing. That's what you do, nothing. So don't do that. Don't have that topology. Have your code in the cloud. Use GitHub, okay? GitHub is not, unlike Eclipse, I've said this a few times, VS Code does not support GitHub natively. But don't worry, I provided complete instructions here on how to get GitHub working with VS Code, okay? So here you go, install these tools. Last tool that I want to talk about is Git Kraken. Totally optional tool. Here's Git Kraken. So Git Kraken is a tool that connects to GitHub, and it provides for me this one feature right here, which is a graph of all the commits that have been done to the repo. And if there were more than one person committing, right now it's only me committing, so I've got my workspace and then the master branch. And so I sometimes do a little test off to the side and then commit it back in, right? So this shows when all the commits were done and who did them, and how the streams merged together. So if you had 4 developers, there would be 4 of these lines in this big tree structure, and you'd know who was ahead of who and how it all fit together. Without that, the native GitHub desktop doesn't have this support. So if you want the graph, get cracking. If you don't want the graph, you can just use the native, you can use GitHub for desktop. I would suggest getting the graph because it's really cool and you can actually see where everybody is. So it keeps track of where the master branch is. And you'll notice, you can't see it from here, but it's got the Toronto Coding Collective icon and my PC here. So when I push something, the PC one will go ahead, and then when I push it up to Toronto Coding Collective, it'll come up and join. So it shows where the remote branches are as well as where the local branches are, and who the different people are. Okay? Enough about Git. So now you've got your desktop all set up, right? So the next thing you want to do is get the Toronto Coding Collective Gyro Drive project. So you've got GitHub desktop set up, and you're just going to go to GitHub. You're going to log into Git. You're going to make a GitHub account, log into Git, go here, right? And if you click somewhere, it shows you how to get there. And then you clone or download, and you say open in desktop, and after, if you followed all the instructions, just bang, now you have it. You've got all this code that I'm going to about to show you. Done. Ready to go. You're ready to run your robot, right? Open in desktop. And then, after that, you want to open the project that you just downloaded. So you open it in VS Code, and it comes in, and then there's this little sort of graph, and it shows you the project. And then you just set your team number, and you compile, and it runs. You've done this, right, Ian?
Yeah.
And it worked for you? You compiled?
Yeah.
No problem?
Into flames.
Pardon?
Hasn't burst into flames.
Hasn't burst into flames.
It's a robot yet, so he doesn't know the robot will burst into flames yet.
Right, yes, right, of course. You haven't had the robot to download to. Excellent. So there's a last step here. So update the VS Code formatter. So Java, everybody has a different indentation style and code style. And normally Eclipse provides this for you. The one in VS Code is totally different from the one in Eclipse. And I know that people are have been programming in Eclipse, and we've developed all this framework in Eclipse. So we had a coding style in Eclipse that we wanted to keep, okay? So what I did was I actually embedded it in this project. So right here, there's a Toronto Coding Collective formatter.xml right there in the project. So here, if I click on this, you can maybe see it better. Oh, I didn't put it. Oh, too bad. Okay, anyway, it's interesting that VS Code doesn't support any way to configure your indentation. What they suggest is to boot Eclipse, configure your indentation in Eclipse, export that, and import it into VS Code. What? That's lame, right?
Why don't we just use Eclipse?
Are you okay with this? Okay.
He's suffering.
He's suffering. It is kind of lame. Like when I found this on the web, I started laughing. Like that's ridiculous. I'm going to install Eclipse to boot it up, to set the formatter, to export it, to import it into VS Code. But fortunately, I've done all the steps except for the import. So all you got to do is import this formatter and set it up appropriately. And there's perfect steps on how to do that. So now you're all set. You've got all the code. It compiles, and you're ready to go. So now you're going to configure this Gyro Drive project, right? And then you end up here, where you can actually run the robot. So Gyro Drive, what is Gyro Drive? So Gyro Drive is the base drive code off of multiple years of programs of the Toronto Coding Collective. So we started 3-4 years ago, and we're here now, right? So what I did was I went and I looked at all the code amongst the 3 years, copied all the common code into one set of routines and put them all together to just make a drive base go, okay? So why did I do that? Well, real-time programming is hard. I kind of discussed that at the beginning, but until you've done it and you run into the bugs, you don't really see how hard it is. But what I see is there aren't people who have the ability to write complex and precise auto patterns. You can't do that. I see robots that look like they're designed really well and they don't behave well. Well, why don't they behave well? Well, our programmers, I hear a lot, our programmers don't know what to do. To Karthik's point, your programmers know exactly what to do. It's really, really hard. It's really hard. So, as a mentor, it's hard to understand what's happening, and I'm not sure how to get to the next level. Like, we don't have an auto, and I'm not sure how to get to the next level. So the Gyro Drive project is an attempt to help everybody get to the next level. The Gyro Drive project is a robot base that has a left-right drive. It's a differential drive, so one set of wheels are chained together, the other set of wheels are chained together, and you've got motors in the middle, motors driving them. You've got an encoder on each side measuring the wheel speed. Okay, so that gives you a nice feedback mechanism. And you've got a compass, a gyro, and you can walk the compass line. Okay? It supports a lot of different speed controllers and a lot of different driver configurations. So what are the key features of the Gyro Drive framework? It helps you get organized. There's a clear place to show your robot map. So your robot map is what ports are all these motors connected to. There's a robot const, which tells us how many encoder counts per inch. Really clear places to feed in these numbers into the framework and then just have it work. Driver I/O, where do I put all those complex driver I/O interactions? How do I see what's up? So someone asked about debugging. How do I know what's going on in my robot? How do I see speed controllers and sensors? Where's the logs going? What are the logs? How do I make a log so that I can see it in the log viewer afterwards and not fill it full of crap? From a functional design, what is command-based it follows the command-based programming thing, and it does great auto orchestration, so auto selections and that kind of thing. So let's look at command-based programming for a second, and then we'll dive right into some code. So here's the WPI lib objective, and you can read that. Basically, they want to make it easy to orchestrate really complex stuff and test it simply. So if I have an intake, I want to test my intake separate from my drivetrain and be able to test my intake and then test my drivetrain and then put them together. So the structure of the layers is this. There are 3 layers. There's an operator input layer, which takes joystick inputs. And there's a subsystem layer, which defines a set of sensors and motors. So in the Gyro Drive subsystem, there's 3 or 4 subsystems actually in this robot. So there's examples. There's a vision subsystem, which is unused, but is there as a shell. There's the drive subsystem itself, which contains the PIDs, the gear shifter for the pneumatic gear shifting, and the compass, the gyro. And then there's another subsystem, which is the pneumatic subsystem, which allows us to turn the pneumatics on and off. So we can turn the pneumatics on and off. Connecting a subsystem with the operator layer are a set of commands. Each subsystem has a default command. There's one command that's running. If nothing else is running, this command is running. So typically that has all the joystick manipulation in it. So the default command is going to read joysticks and do something with the subsystem. If I execute a different command, like let's say pick up this cube command, then I'm kind of relinquishing driver control into the automated system if I have an automated command pickup. So again, at that point, the default command won't be running. The specific command to do the function will be running, and when that command ends, it'll go back to the default, which is likely reading off of the joystick. That's what the default commands are for. Read the joystick input and calculate the elements. Is that clear? Like, does anyone want to ask questions? This is a really complicated idea. Anyone want to ask any questions about that? Your subsystem is a definition of the hardware. Sorry, go ahead. Subsystem is a definition of the hardware. Operator input is what do these buttons do on the controller, and the command is the thing that ties them together. We're going to look at example commands. Okay? All right. So, an example, a command, oh, oops. A command in general has this structure. So I just want to show what a command is. It has these blocks. Basically, I construct it at some point. Here's the beginning, the initial instructions for this command. And that goes in a queue, in a scheduling queue. And when the command's turn comes up to run, the first time it runs the init block and never runs that again. It runs once for this when this command starts. So if this command wasn't the active command, it becomes the active command, it runs the init block. After that, it checks, am I done? And if I'm not done, I run the execute. And then I keep checking, am I done? Execute. Am I done? Execute. Am I done? Execute. Am I done? Execute. Eventually it responds, yes, you're done. Okay, do the last thing and then leave. And then let the command scheduler figure out what's next for this subsystem. Release the subsystem and let the next command take over. So, this is happening at 50 hertz. 50 times a second it's saying, am I done? Execute. Am I done? Execute. Am I done? Execute. There's no time in there for a loop. There's no time in there for a wait block. You can't take control of the robot in this execute block. The only thing you can do is execute if statements. That's all you can do in the execute block. If statements and switch statements. You're doing some logic to set the motor speeds. So at 50 hertz, if we go back up to our other diagram, every 50 times a second, the command is going to read the operator input and set the motor speed. Read the operator input, set the motor speed. Read the operator input, set the motor speed. 50 times a second. Okay? So the complexity there is if you want to do something first for a second and then do something else after that finishes, this is still running at 50 times a second. So those if statements, whatever decision you are going to make, is going to be made 50 times in the next second. So you got to figure out how you're planning your strategy with that. Yeah?
So you can't just put like a wait block in there.
Definitely no. No.
Bad things happen.
That's when your robot starts crashing and gets disabled. It goes out of control. Why is it? I lost control. It's not coming back to my joystick. You can't have a wait block here because you need to read that joystick every 50 milliseconds, every 50 times a second. No wait. Yeah.
So what do you do then?
But you have to plan for the fact that it's going to call you 50 more times. Right? Okay, so what do you do then? All right, so now let's look at some example commands. Let's look at some code. I'm going to try and, here's the code outline, and I'm going to try and show you what the main code is for the robot. So the main code here is fairly well organized, I think. I mean, it's claimed that it is, whether you agree or not, because I'm like that. So here's the beginning and the end of all my robot code, right here. So this is the outline. So this is just the high-level classes, okay? So I've got a camera subsystem. I talked about that before. I've got a CAN drive subsystem, and that's when my speed controllers are connected through the CAN bus. And I'm not going into hardware, I'm doing software today, but the idea is it's a different interface than a PWM interface. So there are two main interfaces to connect your speed controllers with your RoboRio. One is through the PWM drive system, and one through the CAN subsystem. This one uses CAN, but essentially they're the same. I just provided two examples. You can pick whichever example you want to use in your robot and then connect your hardware in that way, okay? There's a power subsystem which allows us to read current off of the power distribution panel, so we can tell if we're over current in a motor. It's not used in this this framework right now. And there's the pneumatic subsystem, which allows us to turn the pneumatics on and off. So if we look at the pneumatic subsystem, it's one of the simpler subsystems that actually does something. Pull this over. So can you read this code? So it begins here, pneumatic subsystem extends the Toronto subsystem. So all the Toronto coding collective classes begin with a capital T. So anytime you see capital T, it's a Toronto coding collective class, rather than one of the base FRC classes. So the base FRC class is subsystem. We extend that to be a T subsystem for various reasons, and we'll get to that in a second. How much more time do I have?
20 minutes.
How much?
45.
Pardon?
123.
So how long do I have?
So, told you, right?
Yes.
37. Okay, lots of time. Great. Good, because we got lots to cover. Is this going too fast or too slow? Should I go fast?
Stick with the space.
Stick with this pace, don't go any faster. Okay. Hopefully you're learning stuff. Okay, so here's the beginning of a subsystem. The first thing we do in a subsystem is declare all the motors that we're going to use, or sensors, or whatever devices. So in this case, we're going to, there's a compressor object. That's the only piece of hardware in this subsystem, is the compressor. It's a compressor pneumatic subsystem, and there's only a compressor. And there are three methods that work on the compressor. The init method sets up the subsystem initially. So if there is a compressor, if it's not equal to null, because sometimes I set it to null for testing, various testing reasons, compressor set closed loop control is true. So that means use the pressure switch to control whether or not to turn the pneumatics on and off. Right? If closed loop control is false, then it says turn it off no matter what. So I can only turn it off, I can't turn it on. Which makes a lot of sense, because you can't turn it on, because what if it goes over pressure, then it starts blowing things up, right? So I can turn it off if I don't want it, but I can only say turn on and then look at your pressure switch to decide whether or not to turn the compressor on. So I've got two methods here, disable the compressor and enable the compressor. And those are actually tied into the operator input layer, and there's commands that filter down and enable and disable the compressor, and we're going to look at that in a second. And then it says init the default command. This is important. So this tells the pneumatic subsystem what your default is. If nothing else is running, run this command. And the default command is called default pneumatics command. Pretty straightforward. And that is under, it's in here, it's in this folder, pneumatics here right now. And then last but not least, the very, very interesting thing here, I think, from the people who are talking about debugging, is the T subsystem extends the regular subsystem, the FRC subsystem, and adds the ability to do this update periodic. And in the update periodic, you want to take information from the sensors and motors that are defined in this subsystem and display them on the smart dashboard. So we've got, if there is a compressor, then tell whether it's currently enabled, and tell whether the compressor is on. So there's two methods here. One is whether I let it go on, and the other one is whether it actually is on. Okay? And then if there is no compressor, then it just puts out false. That's fine. So this update periodic is part of my 50 hertz loop. So every 50 hertz, it's updating the smart dashboard. So the smart dashboard is a buffer here that gets sent over to my driver station, and my driver station is over here. And on my driver station, here I know whether my compressor is enabled and whether it's running. I'm going to put those up on the dashboard. So that is directly linked to the code. Let's go through that again, because it's really important. here's the code that's running every 50 hertz. It's doing update periodic every 50 hertz, and it's updating the smart dashboard values, right? And then over on the smart dashboard, I've got, these are the two values that are getting displayed here. It's showing the two Boolean values here. So if I enable the robot, see if he stopped. Okay, so I'm going to enable the robot here just so that we look at it again. So it's printing out debug information here. This is a debug window in the dashboard. There's a debug window here that displays messages. And you can clear that window or display the level of messages that you want. So I always set it to prints, so that way any system out print line within my robot is going to come here. Now you can imagine if I put system out print line on something that's executing 50 times a second, I'm just going to flood this. It just flies by at 50 print lines per second, which is not all that useful. It's really hard to find information in that. So the smart dashboard is much better if I put for things like that, because on the smart dashboard I'm now going to be able to see the values. So now I'm going to enable the robot here, and the compressor is enabled, right? So now we've got, it shows the compressor not only is enabled but it's on, and you can hear it on, and I've got a control that shuts it off. So I've got a compressor toggle, and you can hear there's an air leak. That's why I shut it off all the time. So here it is on, there it is off. So this is an interesting idea of having a toggle attached to a button. So what it is this joystick. I'm pushing the joystick in. But I've also created an interesting feature here is a toggle. This does not come as part of the WPI package. The idea of pushing a button in and having it turn on, and pushing a button in again and having it turn off. You can read the state of the button, but you can't do this. Like, this is not part of the package. But the Toronto Coding Collective gives you classes that you can turn a button into a toggle like that. Okay? So do you see, you can see that piece. So now how did you get from that button to the toggle? Turn this off. So I've got my methods, my init and my update, enable and disable methods. If I go into the pneumatics command, we talked about the command structure. So I've got my default pneumatics command extends a tsafe command, and we can talk about that in a minute. But there's some debug information, like I want to know what the command name is, and it just gets the class as the command name right now. And then it prints, there's some other stuff. But the execute loop, so then it does the initialize that we talked about, and it initializes when it comes on, and it does this execute loop every 50 times, 50 times, right? So all it's doing is it's saying, give me the OI compressor enabled function, and if it's enabled, turn the compressor on, else turn it off. So you notice here it's turning it on and off 50 times a second, right? That's what this code does. It's going to run 50 times a second, turning it on or off, depending on what comes from the operator input layer. What's coming from here, this get compressor enabled. So I'm going to follow that feature. I forget how to do it in VS Code. Go to definition. Yeah, get compressor enabled is in the OI layer. So the operator input layer has a game controller that's a driver controller that's a new Logitech game controller. So now what if you had a PS4 game controller? that's okay. Just say new game controller PS4, new game controller Xbox. The Toronto Coding Collective is excellent in this way in that it understands that what the button map is for a game controller. So button A, unfortunately on all these different game controllers, these buttons and these buttons are all different numbers on all the different game controllers, which totally sucks because if you have to borrow somebody's game controller, there's not an easy way to change it. You have to go through all your code and figure out how to remap it. But if you're using the Toronto Coding Collective and you need to borrow somebody's game controller because yours broke, you just switch it to the right type and you're done and your code just works. Okay, so what button am I getting? Here I'm getting a compressor toggle.get. Well, the compressor toggle is right here, is defined as a new toggle on the driver controller, and I'll scroll over so you can see the rest of the declaration here. Driver controller, the stick on the left. The speed PID toggle is the driver controller stick on the right, which we're going to get to when we do the speed PID. I'm going to talk about PIDs in a minute, right? So the driver controller, the stick on the left, if I push it, it turns the controller on and off because its toggle function does that. Now we talked about updating periodically. In order to do that toggle, I actually have in the OI layer, we actually have the same idea of the update periodic. So here it's doing a compressor toggle update periodic, because which you have to do because every 50 hertz you got to read that button. Because I only want to respond to the button if it's pressed and last 50th of a second I came through, it wasn't pressed. So if this time it was pressed and last time it wasn't pressed, then change the state of the toggle, right? Because that's how the toggles work. So I have to release it again before pressing it again actually makes an action again. And the only way to do that, again, real-time code is really complicated. The only way to do that is to keep track of the state and everything, which you could do in the default pneumatics command, but then it's not reusable code. So we made a toggle class, and you can feel free to explore that toggle class and see what it does. However, the point being that the update periodic updates all the toggles and then displays values on the smart dashboard. Right? So then we see those values again on the smart dashboard. There's a set of toggles here: compressor toggle, speed PID toggle, driver rumble. Right? So it's got rumble control as well. You can figure out the rumble control. I don't use it for anything right now, but you can see that there's the speed PIDs on and off, there's the compressor on and off. So you can see these toggles are the two buttons, the stick left and stick right, that are coming on and off there. And that's done in the operator input layer. So I'm in the operator input class here, oi.java. I've got these toggles and I'm putting them out on the smart dashboard. So this shows you that anything you put on the smart dashboard, you want to be updating every single loop through. So you want to find those update periodic methods, insert your smart dashboard and statement, and then it just automatically shows up on the smart dashboard. There's nothing else to do, it just shows up at that point. Then you get this. Now, it shows up in a bit of chaos, and so then what you have to do is you have to drag and drop all the pieces, but the smart dashboard is really easy that way. You can just pick up a piece in the smart dashboard and move it somewhere else. See that? Pretty straightforward. So pieces show up, and you can move them around and set up your smart dashboard the way that you like. Fortunately, in the Toronto Coding Collective, I've given you this smart dashboard. Right here, it's called shuffleboard.json, and there's instructions on how to load that JSON file into your smart dashboard, shuffleboard, and it gives you the layout that you see today, like that exact layout, right? So now, this is boring. Are you guys bored? Everybody's kind of sleepy. Should I pause for a second and do some question and answer? Do you want to drive the robot around? I don't know what to do. Should I keep going? There's lots here.
Yes.
Okay. So I mentioned at the beginning organization. So I talked a little bit for debugging person. You've been paying attention to the debugging. This is your smart dashboard. We're going to get to the log in a second, the idea of logging information. But before I do that, that's another way. I want to show you how to organize your code. So there's two key files here: the robot const and the robot map. The standard FRC stuff comes with an empty robot map. Mine's filled in, so it shows you how to do it. The robot const is another idea altogether. So robot map right now looks like this. I'm going to make it just slightly smaller. Sorry about that, because I just want this to all fit on one page. Can you still read that, or is it too small? So. Okay. So it's too small? Yeah, I'll blow it up again in a second, but I just wanted to be able to get it on the width here. The idea with the robot map is that you want to tell the robot where things are. So this one, if I read this out, it says can speed controller address 3, can follower speed controller address 4. So address 3 is my my left drive can speed controller, and my left drive can follower is at 4. The type of the speed controller at 3 is a Talon SRX. The type at the 4 is a Victor SPX. So the system will then know where the motors are and be able to set them up appropriately. And that relates back to our lovely Internet Explorer page, where I've got a Talon here on the left, and unfortunately this one doesn't blow up. I tried to hit the Control Plus and it won't get any bigger. I'm sorry about that. This one's a Talon SRX, and then there's a Victor SPX follower, and the numbers map. The left here is 2 and 4, the right is 1 and 3. And this shows you how important it is to be able to, right is 3 and 4. 1 and 2 and 3 and 4. This is text that you can just type in, and this here is the actual address. So the address is 1, and this text could say left primary motor, right primary motor on Talon 4. And you wouldn't know looking at this list what's on what port. So put the port number in the description, or else you have to click through and figure it out every time what's on what port, if you know what I mean. So when you configure the address here, actually put it in the description so you can read it here on the description, because it doesn't show automatically what's on what port. But these ports, 1 and 2, are the left primary and the left follower, both Talons. On the other one, we had a Victor follower, and so you can either have them the same or you can mix and match, right?
Yeah, Richard, I just want to interject for a second that for the people who are doing debugging, that tool can be really useful in a competition, because CAN bus is a daisy chain, and if there's a break in the chain, you look and say, oh, a CAN bus device is missing. And that'll tell you, I see 1, 2, 3, 4, 5 is missing. So you know that the connection between 4 and 5 is not there. And so for people who are debugging or in competitions, that's also a good way of telling them the physical state is there.
Definitely. That's a really great point. Really, really great point. Yeah, it's one of our debugging tools. So now I'm going to blow this up. And then below is the exact same idea, but just with all the PWMs. Because remember I said I gave you a PWM example and a CAN example? So normally you would just delete one of these and just use the one that you're actually using. You wouldn't have 2 sets of these addresses. So that's better, right? So there's my CAN. There you go. That's better. So there's the CAN constants. And what I've done in this is this is all in a static, again, Java people, I'm not going through too much Java, but it's in a static constructor here. And the idea here is that we have multiple robots, and they might not be wired the same, and for whatever reason I might not even have you know, enough CAN devices to do it all CAN between my various robots. So here it's switching on a robot const that says which one, whether it's a test robot or a production robot. And right now in here I've only got test. I've only got a test robot. But that goes, so this is the robot map, and then it goes to the robot constants, which define other constants around your robot, like which robot it is. Where does it define the robot? There it is, test robot and prod robot. So right now we're on test robot. If it's, those are the two that I've defined. And then, sorry, I'm scrolling down in the file because I don't have enough room to display it all. So in this case, it's saying that the robot that we're using is the test robot, and on the test robot, the max low gear speed, max high gear speed, PID constants, and encoder counts per inch should be there. Yeah, yes. And encoder counts per inch are the 5 constants that I need. Those are the set of constants that I need in order to run this robot. I need to know what the maximum speeds are, and what the proportional and integral gain constants are for the motor controllers and the encoder counts per inch. Because if I want to say drive to this many inches, I need to know how many encoder counts to stop at, right? So it's got to have that division to be able to translate between inches and encoder counts. And this framework has all that, those ideas built in.
Richard, do we ever update the encoder counts? Do we ever update the concept based on like, if the wheels start to wear away from the beginning to the end of the season?
We do by using a measuring tape. So what we do is we would run the robot a certain distance and then take a measuring tape and then look at the encoder counts that are displayed on the smart dashboard and then update the constants. So we have done that before. Mostly because it's not all that accurate in general, but it's accurate enough to score great autos. Okay, so I took you through the pneumatic subsystem. One thing that I wanted to take you through is the drive subsystem, what the drive subsystem looks like. So this is the CAN drive subsystem as opposed to the PWM drive system. And what it does is it defines the speed controller on the left, the speed controller on the right, what gyro I'm using, and then the gyro PID constants. Then because it's a CAN bus device and the encoders are connected to the CAN devices, I have to get the encoder off of the CAN device. So it says get speed controller on the left side and get the encoder attached to that, and that's my left encoder. And my right encoder is the other. Then I set the encoders on the subsystem. In the case of a PWM, they're attached to the DIO ports, the digital input-output ports, directly on the RoboRio, and you can define it all in the constructor, and there's the good example of that. So this is all that's required to define the subsystem. Now you would say, well, I don't need that because I'm going to do all that in the robot map and the robot const, and then I'm just going to leave this the way that it is. And that's great. And there are only a couple of methods in here, enable turbo and disable turbo. And you can imagine that they go to the default drive command. The default drive command says, is turbo enabled? Okay, enable turbo. Is turbo enabled? No, false. Disable turbo. So the turbo is attached to the bumper here on the robot, and if the pneumatics weren't leaking, I would show you it shifting gears. But of course the pneumatics are leaking. And then the last thing that is I want to print on the smart dashboard is the turbo enabled. So that's that other button on the smart dashboard of whether turbo is enabled or not. So if we go to the smart dashboard, maybe too fast, but and the robot's enabled, and I click this button, it shows that the turbo is enabled up here. And if I had the compressor on, I don't know if I can build up enough pressure to fire it, but you can hear it's trying to fire. firing, and then it would switch gears as it was going.
What is a turbo? Like, what does it do?
So I've got a 2-speed transmission with a high gear and a low gear, and the turbo kicks it into high gear.
Okay, okay.
So as you're driving, it kicks into high gear. And you could hear the pneumatics trying to fire there. That was going to drive the turbo. So, okay. So now I want to go to the commands. And in the command, this is not the greatest view, is it? So I've got commands for the drive system, the default drive command, and in the Toronto framework, there's some more commands. So in the Toronto framework, under the gyro drive command, I have the default drive command, but I also have a drive on heading command, a drive on heading distance command, and a rotate to heading command. So there'd be drive on heading would allow me to say in my auto, drive this distance on 0 degrees, turn to 90 degrees, drive this distance at 90 degrees. So what that means is that I'm taking an absolute trajectory as I'm going along. I'm driving at 0 degrees, I'm turning to 90, and I'm not just driving straight now, I'm actually driving at 90, and that 90 is in reference to my original starting point. So if this turn was off slightly, as I start to drive forward, it's still going to correct onto that new heading. So that enables you to write much more accurate patterns, right? Because even if you're off by a degree or two when you make the turn, you're going to now track that new heading when you go on that new direction. So by using these commands, I can write a fairly complex auto. So the pattern here has an example auto command. So it's got an example auto selector, and then under the commands, it's got an autonomous command. So here's my autonomous command. Actually, I should show you on the Smart Dashboard first the idea of the auto patterns. I've got 3 auto patterns. I've got go straight, turn in a box, go in a box, and go straight with no PIDs on. So that way I can show you that I could, like, you know, if we wanted to, we could run it, and I could show you the difference of no PIDs versus having PIDs. And then I could show you the whole box thing. And when there's PIDs on and you're tracking the gyro PID, you kick the robot and it actually corrects. Like it goes back to where it was before. You can't knock it off course. It will stay on course. Okay? So I've got these 3 straight boxes and straight with no PIDs. So what does that look like from a code perspective? And here's where the magic, this is the magic for you guys. Okay? I've shown you how there's code here that shows you an auto selector and how to get those selection values up on the dashboard. I've starting position, left, right, center. Pattern is go straight, straight, no PID, a box. How to set all that up and how to have it come up on the Smart Dashboard. Great. Now I actually want to run the auto command, and I want to write simple code. So if the pattern equals go straight, add this sequential command, drive on heading, distance command, 250 inches, 0 degrees, 0.95 power, timeout after 15 seconds, break at the end. You can stack these up now. You can design an auto pattern that actually drives where you want it to go and stops when you want it to stop and does exactly what you want. The second pattern is drive straight with no PID. Now, I don't have something that has no PID, and if I've got no PID, it just goes by time. So drive on heading, distance command. Oh no, this one has, no, this one. Drive for time. Drive for time, 0.95 speed, 6 seconds, break. That's all it does. So it's got no measurement, it's just gonna drive for 6 seconds at 0.95 speed and then stop. Break when finished. Third pattern drives in a box. Sorry. Third pattern drives in a box. Add sequential, drive on heading distance, 36 inches, 0 degrees, 0.5 speed, 5-second timeout. Yeah?
What other parameters we have are the brake when finished?
Coast when finished.
Or what does that mean?
So it just doesn't turn the motors off.
Oh, so
Like it just goes to the next command without turning the motors off. It just coasts in between, right?
okay.
So this one drives on head 24 inches, 0.5, coast when finished, so it just leaves the motors running. And then the next part of it is driving a 3-foot box. So it goes forward 2 feet first, and then it drives forward, turns, drives forward, turns, drives forward, turns, drives forward, turns, and stops. That's that auto pattern. And that's built in, you can just run it. After you've tuned the pins, then you just run these commands, and it shows you how to do one all the way down, okay? The reason that we pass in the robot OI and drive subsystem you need, but obviously if it's auto, I'm not accepting any robot input command, any OI commands, right? However, the T-safe command, if I'm reusing this code in teleop, I want that feature because I've coded the back button here to can't always cancel every command. So the T-safe command gets the cancel off of the operator input and cancels whatever command is running. So if I'm running some other command, like I have a rotate to a position command, and right now it's up on blocks, so if I try and rotate to a position, it's either going to time out if I wait long enough, hopefully it has a timeout, 5 seconds. But if I don't, I'm trying to rotate, obviously it's not turning, you can't get to that angle, I can just cancel it with the back button. So that's just built into all the commands, that the back button automatically cancels whatever command is running. So now, debug, I want to go quickly to debug on this. Each of the commands there's a lot of information, right? It's overwhelming, but it's all on the Kernel Coding Collective site, so you have it there, right? Go there, go and learn. Default pneumatics command, you see here that I've made a string out of the command name. So this command, this is called default pneumatics command name, right? Get simple name. So what this does is it takes the class in Java and it gets the simple name. So it strips off Kernel Coding Collective whatever, right? So it strips off all the header and you just end up with this string. So why do I want that string? Well, I want that string because I want to do get command name, return command name, right? And so I want to get that command name. And I also want to get whatever parameters were passed in. In this case, there are no parameters, so it just gets the super of whatever parameters were passed into that. But here's the key. On the initialize, remember I said that initialize only ever runs once, and we don't want to flood our logs with extraneous information. On the initialize here, if the command name, get command name is a call that everybody answers, is equal to this command name, in other words, I'm the command that's running. I haven't been extended by somebody else. It's not somebody else that's extended me that's running. If I'm running, then I want to log a message, and we've written this in the safe command. Log message. Get the parms, get all the parameters that this command was using, and print out starting. And then at the end, it also prints an end, and I forget. Oh, it automatically does that as part of the end. It gets the command name that's running and prints the end, prints that it ended. So what does that look like in our system? So what I want to do here is I'm going to run a box auto from our system. I'm going to clear the logs. And then run a box auto. Box, yes. So that was annoying because everything timed out because it actually couldn't turn. So it was trying to make these turns and allowing 5 seconds for each turn, and it couldn't do it. It couldn't get there because I've got it up on stilts. Otherwise it would have turned and ended right away. But then the question is, what happened in the logs? So there's a couple of things that I want to show you here. I can view the log file, go to the event list, and what happens here is it prints out the auto command configuration in the log, and then it starts printing out what it did. In auto, it did a default drive command, then it did a drive on heading, then another drive on, then the drive on heading, another one, So you can see each command as it started to execute, and every command as it ended. If I look at the more detailed log here in the system out print line, you can see that, and maybe you can't, but it says auto rotate to heading command, current heading is this, rotate to heading command timed out after 5.02 seconds. Then it did and it ended at a heading of 359.9 with an error of 90.12 degrees. So it's printing exactly what it was trying to do on every single command is coming out here, so that after the match, you're back in your base, and you're saying, hey, what happened in that last match? Here's all the commands that got executed, one after another, including the operator commands, including everything. You can tell exactly what the driver did and what buttons were pressed in what order if they fired off commands. Now, I'm not flooding this with joystick movements, because why do you want that, or turbo on off, but it wouldn't be that hard to write a turbo on off and plug that in here. And then you would have not only the smart dashboard, but you end up with this log, and the log of when all the commands started and ended.
Is that a stack trace at the bottom there?
Kind of, it's a system out print line, it's a console.
No, I mean the green text, like that's.
Oh, yes.
Stack trace.
Yeah.
Why
Yeah,
do you
yeah.
do- What's the point?
So what's going on here is the power, I forgot to mention this, on the there's a bug in the power distribution module right now, and I'm hoping they fix that with the next firmware. And what happens is every once in a while, every so often, you'll see this print up, it prints a warning that the CAN communication timed out on the power distribution panel. And that's a known bug, and it's been going for like 2 years, and I hope they finally fix it.
So is that bottom piece, like is everything on that top log being put in the bottom window, or?
More the other way. So this is the real-time log, this is a history. So now I can go back through the history of all the matches that I've ever run over many, many days,
Okay.
and see the log history of all the matches over many days. So it's the other way around. This is the real-time, this is the log, this is the historical log. Okay, and you get to that,
So if you took out all the stack traces, it would look the same as that stuff up there?
Yeah, it was
pretty close.
Pretty, okay.
Pretty close, not exact, but so for instance here, yeah, it's got like rotate to heading command, you know, a bunch of other things. But at one point it says I printed out the auto pattern that was used, and I don't know if you remember, but in our auto pattern there it prints out a bunch of lines here. I'll go back there. In our auto command at the top, it actually prints out what the robot positions that was selected and which pattern was selected. And in the log, it just says, I'm printing the auto configuration. I don't know how to drill into that, but you should be able to, because these all have the exact same timestamp, because it just goes, then it sort of logs them together from a historical perspective. And maybe there's a way that you can drill in there and actually see all this stuff, but on the log, it just says auto command configuration, I think. I haven't really got it too far into this, because this was sort of a little thing that I came up with the other day, and I thought, oh, that would be really neat if we had a log of everything that was going on the robot.
Because last year I think it was really hard to get print statements coming off the robot, right? Like if you just wanted to log.
See there, it's printing the auto command configuration. It doesn't show what the configuration was. Like it doesn't show the rest.
Like what generated that blue line there? Like how? Like where did that come from?
The system out print line.
But you printed more than that though.
I did. I agree. I printed
just
more
cut-
than that.
cut
Maybe.
off.
I don't know. I don't know why this does this. And maybe there's a way, you know, I need to explore it a little bit more and see how I can get this to go into the more permanent log. Down on the driver station, in those logs on the driver station, it prints every single time. Really what I need to do is disable the power distribution panel that's throwing these CAN bus errors. And so then that way it doesn't flood the logs with crap. And then you'll be able to see it all. So that's another magic sort of piece of debug that, you know, here's a structured way to get command information coming out on the console and in the logs every time. So now I think I've only missed one piece of our questions, and that is, can you show me how to tune a pit? That was.
Before that though, I have to get back talented for a soccer game. So I just want to say thank you for this presentation. It really helped out. What was it? Jitter, I can contact you through that though, right?
Through Gitter? Yeah.
Okay.
Sure.
Alright.
Yeah, send me a message through Gitter.
Thank you for your help.
You're very welcome. Sorry. And now kids, and then we wrap it up because it's late, right?
Well, there's no other panels after this.
Everyone, whoever doesn't want to see kids can go. I know it's been long and it's late, right?
I like your box.
What's that?